Section 2.2, the inverse of a square matrix n by n. This is the section 3.5 in Edwards. Suppose we have two square matrices and A and B, we say A and B are inverse of one another if this definition holds true, meaning if I multiply A by B or B by A, I get identity matrix. What's an identity matrix? Is a square matrix which the main diagonal elements happens to be 1, off main diagonal elements happens to be 0. The beauty of identity matrix is if you multiply it by any matrix, regardless of the order, you get the matrix back. It's kind of like reduced row echelon form of a matrix, except it's a square matrix. So if you can find a matrix, like let's say B, such that regardless of how I multiply it, this is called right multiplication, this is called left multiplication of your given matrix, and you get identity matrix, then we say B is the inverse of A. Okay, or you could say A and B are inverse of each other. The notation for inverse is what? This guy right here, with A as superscript -1. Please do not read that at A to the -1 power. Read it as A inverse, A inverse. So we say A is invertible matrix if A inverse exists. So invertibility means existence of the A inverse. The reason we say that, because not all the matrices have an inverse, all right? If they don't have an inverse, then we call those guys non-singular, whereas these guys are called singular matrix. Do you see it? Okay. Question, could you verify to see if B is the inverse of A? And these are the matrices. So by definition of the inverse of a square matrix, if it exists, that is, this equation should hold true. In other words, A times B should be identity matrix, B times A should be identity matrix. Notice if I multiply A by B, this is what? 3 by 3 matrix, and that's also 3 by 3 matrix. I get 3 by 3 identity matrix, checks. But that's not good enough. You also have to check the other direction, B times A, and that also gives you identity matrix. Therefore, we say, aha, matrix B is inverse of matrix A. As a matter of fact, I can come back here and call this A inverse. Do you see it? Because this guy is the inverse of this. How did I know that? When I multiply these two matrices together, regardless of the order, I came up with identity matrix. What's an identity matrix again? It's a square matrix whose main diagonal elements happens to be 1. Off main diagonal elements are 0. So now 6 important facts. It is notable. It's important to make a note of. 1, the square matrix is invertible if and only if rank of A is the same as number of variables. You know what rank of A is. Rank of A is what? When you put the matrix in row echelon form, count the number of non-zero rows. If that's the same as what? Number of variables, then the matrix is invertible, so that means A inverse exists. A matrix does not have an, Square matrix does not have an inverse if it has if it has rows and columns of zeros. So if you have rows and columns of 0 in any square matrix, you can bet your money that matrix has no inverse. Also, a matrix has no inverse if any row or column is a multiple of any other row or column, or if they happen to be the same row or column, then no inverse. So if any row or column is a multiple of a different row or column, which that implies a special case, like what? If they happen to be same rows and same columns, you have identical rows and what columns in both matrices. They are not inverse of, I mean, in the matrix, it doesn't have an inverse. If A inverse exists, then your non-homogeneous what? System of equation has a unique solution. How about that? You can, tell if a system of linear equation has a unique solution or not simply by check and see if the matrix of coefficient is what? Invertible. Then again, if the determinant is not zero of a square matrix, then A inverse exists as well. But then again, stay tuned for next section, which we kind of go over what determinant is. All right, some properties of inverse matrices. If you do have an inverse of a square matrix, so then these three observations are important to make a note of. So if this A is invertible, that means A inverse exists. Okay, so if A is invertible, then guess what? Then inverse of A inverse is A. If A times B is invertible, then A times B what? Inverse is B inverse times A inverse. Notice the order I have to switch. AT is invertible, what? The inverse of a transpose of a matrix is transpose of the inverse. These are three important rules of properties of the inverse. But how do you find the inverse of an invertible matrix? Okay. The idea is if you can take a matrix and via row elementary operations change it to identity matrix, that matrix has an inverse. So if you reverse the process, you get the A inverse. In other words, going from what? Identity back to what? The matrix itself gives you the inverse. Case in point, here's what we do. Suppose I give you a square matrix, 3 by 3, and I want you to find the inverse. So what you do, you make this augmented special matrix. You put the what? Matrix A on the left side and identity matrix on the right side of this vertical line. I'm right here. Go through what? Row echelon form, in this case, reduced row echelon form, correct? And I should say reduced row echelon form because I want this format, main diagonal elements 1 of main diagonals of what? 0. So that's a special reduced row echelon form which is called identity. So converting this via what? A row echelon form to put the final answer in reduced row echelon form, it transfers the identity matrix to the left side of the vertical line. So whatever is left here is your A inverse. In other words, the inverse of this matrix via this steps is this. So how do you check that? Well, multiply it by original matrix, regardless of the order of multiplication. Make sure you get identity matrix. So the beauty of it is, if A is invertible, it has a matrix, you can use the inverse to solve a non-homogeneous system of equations. And you can find its unique solution. How? If AX is equal to B and A is invertible, that means A inverse exists, you can multiply both sides of this equation by A inverse, left multiplication. But A inverse times A is identity, okay? So that's I times X equals A inverse B, but I times X is the same as X, and X is the solution to this non-homogeneous equation. So here's the formula. It will be nice if you remember it, which is if the matrix of coefficient is what? Is invertible, that means it has an inverse. Find its inverse, multiply it by the what? Column vector of constants. Lo and behold, you get the solution. So what does that mean? Suppose I was asked to solve this system of equations. 3 equations, 3 unknowns. Remember, you gotta have a square matrix, otherwise There is no way you're going to find its inverse. In other words, in terms of system of equation, I got to have same number of equations as I have what? Number of variables, nothing less or more, yes? Find the inverse of coefficient matrix, okay, which we already did right here in this example. I chose the system so it would match this matrix. You know, these are the coefficients of my unknowns. Multiply that inverse by the column vector of constants, and lo and behold, you have your unique solution. In other words, the solution for this system is what? 5 over 7, 3 over 7, 2 over 7. How did I get it? By multiplying A inverse times B. Keep in mind the order matters, so you got to multiply A inverse by the column vector of constant. Otherwise, you'll have a dimension problem. You see it. Additional properties of A inverse. So it will be nice also you remember these. So a square matrix is invertible. That means A inverse exists. Okay. Null space is what? Of matrix A is what? A space containing what? Nothing but zero vector. We're going to talk about this. If rank of null space is 0, then what? A inverse exists. If the null space of matrix A is what? Nothing but 0, which that pretty much means this. Okay, that means A inverse exists. Columns of A or rows of A form a linearly independent set of vectors in Rn. So if A inverse exists, columns of A or rows of A form a linearly independent set of vectors in Rn. Column space of Rn is spans Rn. Row space of what? Of matrix A, rows of A spans Rn. Rows and columns of A form a basis for Rn. Stay tuned for a few more sections so we can talk about basis. A transpose is invertible. That means A transpose has an inverse. When you have non-homogeneous system of equation, this will have a unique solution provided what? A inverse exists. Okay. Homogeneous system of equation has trivial solution. Trivial meaning what? The solution, the one and only one solution is 0. If what? A inverse exists, which means determinant is not equal to 0. Rank of A is the same as number of what? Variables. And determinant of A is not 0. If any of these what? Let's say 2 through what? 11 properties hold, then what? A is what? Invertible. And that's pretty much about inverse of a square matrix. Keep in mind, not all the square matrices have an inverse. That's one of the reasons division is not defined when it comes to matrix operations. Thank you.